Hey guys, this is myself 06, and in this video I'm going to talk about how I made an NES emulator for the SNES. And as you can see in the background, this is how it runs, at least for some games. Not every game runs on it. So I'm going to talk about some of the differences between the two hardware, as well as some of the challenges I had to face. So first, let's take a look at the differences between the two hardware. So we have a 6502 versus a 65816 CPU, which is a future generation of the 6502. It also comes at double clock speed, but the 65816 not only can operate in 16-bit mode, it also does what the 6502 does, but better. So it's more or less the same instruction, with some exceptions. So we have emulation mode to restore some of the timing and some of the page wrapping rules. However, enabling emulation mode comes at huge costs. So in emulation mode, when an interrupt happens, we lose 8-bit of a program counter, which points to where the code is running. And if we need more than 64 kilobytes of code, we are losing which bank code resides in. In other words, we need to spend extra time to fix this problem. So emulation mode, while yes, it does fix some problems, it creates bigger problems. So next is the RAM, the system memory. We have 2 kilobytes versus 128 kilobytes. So huge improvement, but the RAM on the SNES, you may notice that it runs slightly slower than the CPU itself. So we have a penalty of 1/3 of a cycle each time we access RAM. Next, for the DMA channels, which is direct memory access, there's one on the NES. It's for OAM only, which is object attribute memory, otherwise known as sprites. So when updating sprites, we use the DMA and updates everything. Read-write, it's read and then write at same clock speed as above. So it only transfers 1 byte every 2 cycles. Whereas on the SNES, it's read and write, but at a lower clock speed. DMA can either happen immediately, or on the SNES, it can happen at each H blank, which is horizontal blank, which is the period of time that the TV waits between each line. So we can change things like scrolling, character changes, window changes, brightness. Next, we're going to look at TV resolution, which is 256 by 240, but on the SNES, it's slightly less at 224 scan lines. But there's also a mode that allows just one scanline short of the NES's resolution. So that's what we're using on Project Nested. However, if you run this emulator on SNES emulators that do not support this mode, such as SNES 9X, you will be missing some scan lines at the bottom. And then we have 56 colors, which is supposed to be 64 colors, but some of them are either black or even darker than black itself, which can cause some problems with some TVs, so avoid using those. And then on the SNES, we have 32,000 colors. This is 15 bits of colors. As for palette choices, we have 8 palettes of 4 colors each. One of them is always transparent. On the SNES, same thing, but 16 palettes of 16 colors each. Again, the first color is always transparent. Next, we're going to talk about background layers. So on the NES, there's only one background layer, and it's only 2-bit per pixel. So we can only have 4 colors within each tile. On the SNES, however, we have different modes. I use mode 1B. Mode 1 has 3 backgrounds, but some modes have anywhere from 1 to 4 backgrounds. Bit per pixel is always 2 on the NES, but can be 2, 4, or 8 on the SNES. So for mode 1, the bit per pixel are 4, 4, and 2 for all of their respective backgrounds. background resolution can be 32 by 30 and then duplicate either horizontally or vertically or both. This one I believe requires some mappers in order to achieve, but most games use either of these most of the time. On SNES, we have 32 by 32, and again, double horizontally or vertically, or both of them at the same time. But notice that we have two more tiles vertically. That's the equivalent of 16 pixels. And while this is not directly compatible, there's actually HDMA that can help us trick the system into skipping the last two tiles. Next, we have number of characters per background. So on the NES, we have 256 characters to choose from for the background. On the SNES, we have 1024, which is not going to be very relevant for this emulator. The VRAM is 2 kilobytes plus whatever is in the cartridge. On the SNES, it's 2 times 32 kilobytes. So what they did is use two 32 kilobytes RAM able to output 8-bit at a time instead of a full 16-bit RAM. And the reason they did that was for mode 7, which can access the two RAMs at two different addresses, but every other mode will access RAM at exactly the same address, and combining the data as if it was one whole 16-bit. If we scroll down, we have objects, which are also known as sprites. So the number of sprites on screen is 64 versus 128. Bit per pixel is 2 on the NES, 4 on the SNES. There's no other option here, which is going to be relevant for this emulator. Number of characters, we have access to all 512, of which 256 are shared with the background. On the SNES, it's 512, but it is not necessarily shared with any background. Object size can be 8 by 8 or 8 by 16. On the SNES, it's much different. We have 8 by 8, 16 by 16, 32 by 32, or 64 by 64. But we can choose two of those sizes. There are two more sizes to this, but those are not official. So here, as you notice, there's no 8 by 16 on the SNES. So one way of doing this is to use 16 by 16 sprites. However, we need double the characters if we do that, and the new characters have to be blank. But because we can access 512 characters on both consoles, this is not a very viable approach, and it wastes a bunch of RAM in the process. So what I did here is, instead of using 16 by 16, I used 8 by 8 twice. So one for the top, one for the bottom. Notice that here we have double the number of sprites on screen. So if we use all 64 at 8 by 16, it's using all 128 sprites on the SNES. Number of object per scan line is 8 on the NES, 32 on the SNES. The number of tiles, however, is a little bit different with 34 tiles shown on screen. So we can actually use this to emulate the 8 sprites per scan line by simply using some 64 by 64, which is going to be 8 different tiles for the single sprite on 64 different lines. So if we can overflow this, we can actually emulate this. And while Project Nested can do this, it comes with a cost of having to reverse priority on sprites. So if anything needs to be on top of something else, that's going to be reversed, and the limit is not going to work properly. There are some games using this trick to not show sprites in some certain parts of the screen. So for example, in Zelda 1, when you go through a door in the dungeon, you see Link entering the door. But on Project Nested, if you don't enable sprite limit, he goes over the door and into the next room. Object hit is when a sprite is drawn on screen and the CPU is then told, hey, we have this sprite that was drawn on screen. On the NES, only Sprite 0 has that capability. So anytime Sprite 0 is drawn on screen, the CPU can see that, oh yeah, Sprite 0 has been drawn. So then CPU can choose to change the scrolling. This is done in Super Mario Bros., where the top of the screen has your score, your world, your coins, and then the bottom of the screen scrolls while the top does not scroll. And this is done by having a sprite on the coin at the top of the screen. This is Sprite 0. And once it is drawn, the CPU waits a tiny bit more and then change the scroll value. On the SNES, however, this cannot be done, but there is a trick that I'm using to detect Sprite 0, and instead of waiting for a certain line, we instead identify which part of the code seems to be waiting for something to happen, and just make that thing happen. Next, we have audio channels. So on the NES, we have 5 audio channels, 2 squares, 1 triangle, 1 noise, and 1 delta modulation channel. On the SNES, we have 8 channels that can be pretty much anything with some restrictions. It can also run software, where on the NES, it cannot. So this is great for emulating sound, because we can offload most of the work to the APU, and not much work is done on the CPU. Only about 1.2% of the CPU is used for audio emulation, and then everything else is offloaded to the APU. Then we have controller. 4 buttons plus D-pad versus 8 buttons plus D-pad. The number of bit that is read at a time is only 1, so instead of reading 8-bit or 16-bit or whatever, it only reads 1 button at a time. And there's, in theory, no limit on the number of buttons. So what can happen is, on Project Nested, what I decided to do is give access to the extra 4 buttons to the NES game. So if anyone out there makes a game or a mod for a game, you can actually use the extra buttons on Project Nested by simply reading 4 more buttons. And this is because this is the only part of the SNES that is 100% backward compatible to the NES. It works exactly the same, and so you can plug any controller you want. It will read the extra 4 buttons. But so far, there isn't anything too different about the 2 consoles. But the main thing that prevents emulation is the CPU, because if you look at the clock rate, it's not that great. It's only double speed, and that is the main reason that I thought this was impossible. You can't run NES games at full speed on the SNES. But with some years of casually thinking about it, I realized, yeah, it's actually possible. Here's why I thought it was impossible. So we're going to talk about emulation ratio, which is the number of cycles that your computer has to spend in order to emulate one cycle of the emulated hardware. So in the case of NES and SNES, which are interpreted, we get roughly a 40:1 emulation ratio, which means PC has to spend roughly 40 cycles to emulate one cycle of either the NES or the SNES. On Nintendo 64 and GameCube, which are recompiled, we get a much better ratio at about 10:1, but this is according to my own experience years ago. So in recent time, GameCube emulation is much better than 10:1. And then we have virtual machines, which are basically PC on PC. So you can emulate Windows, Mac, and Linux on either Windows, Mac, and Linux. These are used professionally by website hosting, because hosting a website doesn't take too much processing power, and we gain the advantages of emulation, which is save states and the ability to block access to the entirety of the computer. So we could have multiple virtual machines running on a single computer. And these usually range from 6 to 1 to 3 to 1 based on what you're running, which is pretty good. And because these are professional emulators, it's hard to get better than this. And as you can see below, a 2 to 1 emulation ratio is required in order to run NES game on SNES. This is the reason why I thought full speed emulation of NES games on SNES was impossible. But with some clever optimizations, as well as ignoring timing, I managed to fit a NES emulator in the 2 to 1 emulation ratio. So, timing emulation is ignored. But certain things we can do. So for example, sprite serial hit code will look similar to this. We load some data from an I/O port, which needs to be emulated. Then we mask bit 6, which is the bit that represents whether or not sprite 0 was hit. If it was not hit, we go back to minus. So here, project nested overrides this line and tries to count how many times it was accessed, and after a few attempts, it decides that, okay, I have enough. Let's set something. Let's say sprite 0 was hit, and then the loop can move forward. But while it does that, it also changes the virtual scan line to where sprite 0 is, plus whatever number we put in the settings. So there is a setting called sprite 0 hit offset, which decides how many lines to add to the virtual scan line based on where sprite 0 is. Some mappers can trigger an interrupt request at a specific scan line, just like the SNES, but this is going to be emulated slightly differently. For example, we are not using the real timing, so when the scan line is hit on the SNES, we are not going to trigger a NES interrupt request. But instead, for the non-maskable interrupt, it can happen in two different ways. So we either hit SNES vblank, which triggers a non-maskable interrupt, except I don't use non-maskable interrupt on SNES. And the emulator can also detect idle loops. Here's an example. We load data. If it's equal to 0, we go back, load it again, and just wait until it changes. But this loop has nothing changing in it. So this is flagged as an idle loop, which the emulator overrides by changing this line and executing its own idle loop, which is great because it can count the number of cycles that were unused, so we can see how much of the CPU is actually used on the SNES, but it also can catch up on missed frames. So if there's a bit of lag and there's a frame missing, it can catch up to it by simply skipping over this loop and immediately execute the next frame, even though it's not the correct time. This can be done because there's no timing dependency, and so we can run any part of the code at any time. We can even enable turbo mode, which this thing does, but there's no option to manually enable turbo mode. It's just a way of catching up on lost frames. So what it can do is during slowdown, instead of dropping to 50% performance, it can drop somewhere between 50 and 100. So let's say that the SNES needs just slightly more time. It can drop to about 95%, and the player is unlikely to notice. Now for the expected interrupt order, we have the main thread running, we have an interrupt request, some scrolling values are changed or character banks are changed, then we go back to the main, a vblank happens, and the non-maskable interrupt happens. And then we go back to the main and repeat. When NMI mode at vblank is enabled, we go main thread, interrupt request, and then non-maskable interrupt. There's no going back to the main in between the two. and some games are sensitive to that. So during auto detect mode, we only trigger one interrupt, go back to the main, then trigger another interrupt, and IRQ can be triggered multiple times. Now let's talk about audio channels. So we're going to start with square wave, which is flatline, spike up, flatline, spike down, and repeat. This is also called pulse, and unlike other graphs, I don't like putting a vertical line here because a perfectly perpendicular line is impossible. So if you go from flat line to flat line, not only do you have to break the speed of light, but once you manage that, you then are limited to the universal frame rate, which are two topics that I'm going to cover in future videos. So we have our sample, and if we run it at a lower frequency on the SNES, it gets interpolated. And if we lower frequency again, it gets even worse. And this is not even a straight line, it's like a curve like this. And solution to this problem was to use larger sample, run it at higher frequency instead of lower frequency. But what we can do is run them even faster than they can be output. So here we have slope up, slope down. So you get interpolated all the time. But if we run this too fast, we can actually skip some of the interpolation, which gives the square a much better form than above here, which is something that the original developer for the sound emulator wanted to do, but had never completed. Shout out to Memblers for letting me use his code. His sound emulator is amazing. I made some changes to it, including this higher frequency, but also I changed the triangle. So his original triangle looked more like a triangle, but the NES triangle looks like stairs. It steps up and then steps down. There's 16 steps up, 16 steps down, for a total of 32. There are double the steps at both peaks, and I also added more samples for the triangle because in the original code from Memblers, some frequencies were impossible because it would run too fast for the SNES. So I added more samples for the triangle that can run at much higher frequencies. So since 1.4, every triangle frequency can be played on the SNES. Okay, here's one that I get asked quite a few times is if this is an emulator running on the SNES, why is there a Windows exe as part of Project Nested? So here I'm going to explain what the exe does, but first we need to understand that both the NES and the SNES don't have an operating system. They don't work with files, so all of the data needs to fit in one file. And the only way to combine those files is with an executable on your PC. So here we have a NES ROM. There are three parts to the NES ROM. We have the header, we have the program ROM, and then we have the character ROM. These sizes are roughly what they are in reality. This part here is only 16 bytes, whereas this can be almost 1 megabyte in some cases. Now, when exe converts that, it actually maps this onto here. It also maps this onto here. But it does so in a bit of a strange way. It's not a straightforward copy. So for mapper 0, it is a straight copy. It's 32 kilobytes in there, and then 8 kilobytes in there, so about this large. But then for mappers, let's say MMC1, it takes 16 kilobytes, puts it here and here, so it creates a copy of it, because MMC1 can either see each bank in the first half or the second half of the 32 kilobytes of ROM that is visible to the NES. For MMC3, things get a little bit strange. So we have a bank here, which is then copied here, and here, and here. Why is it doing this? Because the recompiler can't cross banks. And sometimes some games will have banks coupled together that are meant to be together. So for example, Crystallis had problems with this, where some code would cross from one bank to another, but they were sequential banks. For example, from bank 10 to bank 11 are sequential. So if we put the data in sequential order, here, and here, and here, we no longer have this problem with the recompiler. But we also don't lose any performance or anything. It's just reorder how the banks are. If this is bank 0, this is then bank 1, bank 2. And here, it's always a constant, it's always the last bank, because MMC3 can only change the first 3 bank ranges. Now, as for characters, it's a lot simpler. So for every 32 kilobytes of character, we put it there, and then for the next 32 kilobytes, we put it there, and repeat. And then for the header, notice that we have HH here, so it's a little bit bigger, but it's also different H. This is a modified NES header plus whatever settings you have for the game, which are going to reside here at the very beginning of the file. And this is all done without changing any of this data. So the way the game works is not changed whatsoever. Simply copied from there to here. And notice that I left a gap here. This is because in the very earliest version, I had no exe file. I would just put the NES game within this range. And I decided to keep that for every version. I'm not sure if I actually did that, but on 1.4.2, this is how it's mapped. So if you take, let's say, Excitebike, you convert it into SNES. And then you take Super Mario Bros. 1 and you go and open the converted file into HXD or any hex editor. Simply go to this address and paste Super Mario Bros. The entire content will be somewhere here, and the first P here will match first P there. Super Mario Bros. Is 40 kilobytes, so 32 kilobytes of program ROM and then 8 kilobytes of character ROM. This must be done with a 40 kilobytes mapper 0 ROM, and the header must match because this header here is converted. But if it's the same header in case of Excitebike and Super Mario Bros., because they have the same header, this is going to work. You can put Super Mario Bros. On top of Excitebike and Super Mario Bros. Will run. In fact, for the intro of this video, I took Excitebike, converted it to SNES, used a hex editor, went to this address, and pasted Super Mario Bros. This is mainly to demonstrate that this is in fact an emulator, and the exe does not change how the game works. It is simply done by the Super Nintendo, which reads program, recompiles it, and then executes it. Let's now look at some code. If we have a variable at this address and we want to add 8, we load it, clear carry, add with carry this value, and then store it back. On the SNES, it's exactly the same thing because it's the same CPU, but a next generation of it. Things get a little bit more complicated when we do other things. So let's look at native return address. So we have code at this address, and we want to call at address 8123. On the SNES, this can be completely random, and this can be completely random. Instead of JSR, we have JSL, which is a long call instead of a short call. Likewise, we have a short return versus a long return. And this adds some complications to the stack because JSL will push an extra byte to the stack. RTL pulls an extra byte to the stack. So some games are going to crash. And in order to fix them, we use non-native return address. So there's an option on Project Nested exe where you can turn off native return address. What this does is, let's say we have this address calling 8123 on the SNES. Again, this address is kind of random. We push 8002, which is the address of this minus 1. It's very important to keep the stack the same as it was, because non-native means we're using the original address. But because this is at 8000, this is 3 bytes later, because we have the opcode and the operand, which form 3 bytes in total. We're going to push this minus 1, so it's at 8002. Then we're going to jump to the subroutine itself. So it's the equivalent of this, but we push the original address instead of the new address. Then for returning, so the RTS now becomes this. But also, each call creates a virtual label that can be accessed by the code for the RTS. So the RTS itself shares code with indirect jump. So there's a module called JMP-IU, which stands for Jump Indirect Unrolled. And by unrolled, I mean I took a small amount of code and copied it many times to fill an entire 64 kilobyte bank just to have every possibility listed. And this is to boost performance when executing indirect jumps and non-native returns as well. So a non-native return is pretty much the same as pulling 16-bit from stack and executing an indirect jump on it. Next, we have load 0 into accumulator. So normally we load a constant, but in the SNES there's actually a better alternative, which is to transfer the DP register to the C register. So that's what TDC stands for, transfer D to C. The DP register holds the address of where the direct page is, because on the NES it's 0 page, but on the SNES you can move it. However, this value will be 0, or if it's not 0, at least the lower 8-bit of it are going to be 0. C is the full 16-bit of the A register, but as I just said, the low 8-bit of the D register are always going to be 0, and because of that we can just transfer D to C, and that clears A entirely. This saves 1 byte, but also if this is recompiled in RAM, it also saves 1/3 of a cycle, which is not a lot, but this optimization doesn't take too much time. Accessing I/O ports, now we've seen this code before for Sprites 0 hit. What happens is we have a JSL replacing the port itself. So we have read 2002. The A at the end is just a leftover from early versions where every possible load was its own code, but turns out that it's not really the best solution. So I decided instead store the value in IOTemp and then read it however we want. Let's say this is a different opcode, we put it there, and when we put the address of IOTemp here. And then these last 2 lines are just copy of this. In some cases, some IO ports like 2001 is only 1 line of code. So instead, we inline it and it becomes just this 1 line. That's the line of code that is present for emulating this. So instead of calling, executing that 1 line, returning, we instead just write that 1 line into the recompiled code. Now let's move on to reading ROM. Let's say we read at address 8123 with or without index register. First, we need to load the requested bank range. In this case, it's going to be 80. So as I explained before, we break the memory down into 8 parts. This is part of pages 80 to 9F. So we load the range itself, which is 80, compare it to memory NES bank. It's a weird name. I don't know why I didn't change that. This is the active bank range. We use exclusive OR because if we did a comparison, it would ruin the carry flag. So we use exclusive OR in some cases, and then in other cases we can use comparison in case we actually need to push the P register. If they're both equal, we skip this line, which is to change the active bank, because we can only see 32 kilobytes at a time, but this allows breaking the ROM into 8 kilobytes instead of 32 kilobytes. Then we have the original line. We load from ROM and get our data. But what happens if we load 16-bit from ROM? We have to load, store it, load, store it. And this means there are 2 loads to the ROM. But as you can see here, 2 loads are here, and there's only one bank range check. And that's because this is one block of code. And so there's nothing that's going to point to this line without executing this line. It's always going to go from top to bottom as a single unit. And the recompiler understands that, and when it comes to recompiling this, it already knows that the range is set to A0 no matter what. So it doesn't try to verify, oh, are we in the correct range? No, we absolutely are in the correct range when executing this. And then the last one I want to talk about is branch emulation. So when recompiling code, sometimes, as seen above, we have extra code. So that's going to push the branches out of range. And in case the branch is either forward, that means we add it to the PC register, or it's out of range, we instead pair it with a jump. Also, the condition for the branch is opposite. So instead of equal, it's not equal. So that covers how some of the code is recompiled. There's more to it, but these are the most important parts. Now let's move to character ROM bank management. On the NES, the characters come directly from the cartridge, and the cartridge itself can have mappers that decide, no, we're showing these characters instead. So how do we emulate that on the SNES when the SNES only has access to its own internal RAM? First, let's look at how I broke the VRAM on the SNES into these 4 different chunks. We have the background tiles, and we also have 3 sets of the characters for that background. And we also have a debug background, characters and tiles in this range. So each box here is 1/4 of the VRAM. Each set consists of 512 characters for background and sprites. Also consists of request banks and active banks. So the difference between request and active banks is when the game changes a bank, it only changes the request on the emulator, whereas on the real hardware, it changes immediately. So we need to put these requests together. There can be up to 3 requests and 3 active. And then each request is matched to an active set. And the way it works is if an active set matches the request perfectly, those 2 are put together immediately. And then it tries to match a request with the most similar active set. So it doesn't have to transfer too much data to VRAM. It tries to minimize how much data is sent to VRAM as much as possible, because sending all 512 characters during VBlank is impossible. We would have to add a blank line at the top of the screen or the bottom of the screen, so we would miss part of the image just by transferring an entire set. And some games change banks mid-frame, so we have multiple of these sets. Here's a game that uses 2 different character sets on the same screen. What that means is mid-frame, the game will change character banks and result in completely different graphics. So in this case, the emulator will reserve two active sets based on request, and at the top you can see request 0, and the bottom is request 1. The bottom part of the screen never changes from frame to frame, so it reuses the same set. The emulator doesn't need to upload anything, but on the top, every few frames, the character will change a little bit. So the emulator will detect, oh, there is a change, but it matches this character set for the most part. So it only uploads the changes needed. So instead of uploading 8 kilobytes, it only uploads maybe 1 or 2 kilobytes of data every time there's a change. It also depends on the game. Here's another interesting game. This one makes 4 different requests on the same screen. But notice that the playfield is the same at the top and bottom. So these requests will match each other. And also the text box and the HUD at the bottom match the same request. So in reality, while there are 4 changes, it's actually 2 different requests at 2 different times. Here's how the character data is encoded. So we have an image here of 8 by 8 pixel, and we have 4 choices for each pixel: 0, 1, 2, and 3. I decided to change all the zeros with dashes so the image is more visible, because the 0 is always transparent. And then we have 3 other colors. So the way this works is each pixel needs 2 bits, which are divided into planes. So if we take the 3 here, we need a 1 and a 1, which gives 3. For the 2, we have a 0 and a 1. Actually, it's read backward. It's 1 and then 0, which gives a 2. Now, each row of each plane is 8-bit, which only takes 1 byte. So this is 1 byte, this is another byte, and then total we have 16 bytes for this image. The order of bytes goes A0, A1, A2, etc., and then B0, B1, B2. So A0, A1, A2, on the way to 7, B0, B1, B2, etc., B7. On the SNES, however, we have A0, B0, so A0, B0, A1, B1, so it works the other way. So we're going to have to change the order of bytes, but the bits within the byte remain the same. But hold on a second, we need 4-bit per pixel, because sprites can only be 4 bits per pixel on the SNES. So if we look down here, we have 4-bit per pixel SNES, A0, B0, A1, okay, and then we have wait down here, and then we have C0, D0, C1, D1. That's a little bit strange, and that's because it's an extension of what we have here. So we could be using the same characters and just add more bits to it. So what's interesting here is if we eliminate every odd number, so this is at index 0, index 1, index 2, index 3. So every odd number, if we remove those, we get this pattern: A0, A1, A2, etc., then C0, C1, etc. So it's the same as the NES, except we have plain C instead of B, which is going to create something weird on the palette side. But we have the same encoding here and here. So what we can do is upload the NES graphics directly to one of the VRAMs and then zero out the other VRAM. Because on the SNES, each 16-bit or each 2-byte is actually from 2 different VRAMs that are put together. So if we zero one of the VRAM and then upload data in the other VRAM, we get this. We get empty bytes, and we get exactly the same pattern. So what we can do is use this and simply not convert the graphics. We can just straight up upload the graphics on the SNES VRAM and it's directly compatible. Here's one that gets people confused. The VRAM queue is not in VRAM. So, of course, we talk about VRAM queue. What is the VRAM queue? Well, it is a queue of instructions to do during vblank. So how to update the VRAM, change this byte, go to this address, change this other byte, upload this bank of character data, do this, do that. So anything that must be done at vblank is queued at this address. So if you want to poke around, there it is. That's for version 1.4.2. This is subject to change, will likely change in a future version, and this is being accessed with SNES port 2180, which is normally used for DMA, but since I don't need it, I decided to use it as a queue. It's not very useful for anything else because there's auto increment to it, but also you can't read what address it's pointing at. So you set an address, in this case I set this address, and then add data to it. So it just keeps increasing, and I don't know where it's pointing at, so I can't easily verify has it overflown yet. So the only thing this port is good for, other than DMA, is queuing things. So a queue, you write it from left to right, but you also read it from left to right. So in order to read it, we write a 0 in the queue, then we reset the address, then read the entire queue. And the reason we write a 0 is because this is the end of our queue. The very first thing that gets queued is initialize. So a queue can change some of the tiles on the background, can change tile attributes, can change palette. These three are normally the same on the NES, but on the SNES, they have to be done differently. This one in particular takes a long amount of time, and in case the same byte is uploaded, instead of queuing a tile attribute, we queue a read, which increments the VRAM address but doesn't do anything. Same for palette. Changing the palette is more expensive than changing a tile, so we also have a check to see, hey, has the palette changed? No? Okay, let's just queue a dummy read. Then of course we can change how the VRAM increments, also the address itself. Notice that the numbers here are always even, and that's because of an optimization. So when we do indirect jumps, we have 16-bit addresses, and the index to that table needs to be shifted to the left, otherwise known as just multiplied by 2. So instead of multiplying by 2 live, we just do it in advance and just only use even numbers. And here's an example of what the queue looks like when running Super Mario Brothers. So the PPU address increment is changed to 1, which is done multiple times, and after reading this, I realized that, hey, we don't actually need to queue this multiple times because here, for example, it's already set to 1. For transferring sprites, we have a sprite priority. So this one says where the first sprite is. This is only necessary when the sprite limit is active. So if you activate 8 sprite per scan line limit, this is actually useful. Otherwise, it's not. But it's still being put onto the queue because I couldn't bother creating extra code for it. And it doesn't lose that much time. We have an address change to 3F0C. This is the palette RAM, and in there, notice that there are 4 reads here. But as I said earlier, if the colors don't change, we just queue dummy reads in order to not waste time. So what the game does is it updates one of the palettes every so often for coins and question mark blocks, but it uploads the entire palette instead of just one color.
Thank you guys for watching. Please sub, like, dislike, comment, and especially share, and I'll see you in the next one.